addition of real numbers is a commutative operation. So if I give you, let's say, 3 real numbers, it doesn't matter in which order you sum them up. You could sum them up in the usual order, x1 plus x2 plus x3, or you could sum them up in a different order, say x2 plus x3 plus x1, and the result would be the same. Now, more generally speaking, if you have finitely many real numbers, you can change the order of summation whichever way you want. That is to say, you can use any permutation of the finite set 1 to n, right? Any bijection like that. For instance, in the previous example here, the bijection would send 1 to 2, 2 to 3, and 3 to 1, and the final sum won't change. The question we are going to address in this video is what happens if the sum is infinite. Can we say that the infinite series, if it converges, is the same as the infinite series, assuming it converges, of the permutated version of the xj? We are going to prove 2 theorems about this question. The first one gives a positive answer. It says that if you have a series that converges absolutely, then you can change the order of summation whichever way you want, and you will still get a series that converges absolutely, and the sum of that series will be the sum of the series summed up in the standard order. But the second theorem gives a very negative answer. It tells us that if the convergence is there but it's not absolute, that is to say the sum of the absolute values of xj's diverges, then changing the order can completely change the sum. You will still get a convergent series, but this series can sum up to anything you want, right? The statement is that you give yourself any target number, there is a certain way of reordering the natural numbers such that with that ordering, the sum of the x pi j gives you x. Let us start with the proof of the first theorem, the one about absolutely converging series. So I have a absolutely converging series. And then I want to consider an arbitrary permutation of its elements. So I give myself a bijection of the natural numbers. And I want to show that the series of x pi j also converges absolutely, and that it converges to the same thing as the sum of the xj. Right, so let's start with the Cauchy criterion for the sum of the absolute values of xj. So absolute convergence gives me that for every epsilon there exists a capital N that depends on epsilon, such that for every little n greater than little m greater than n epsilon, the sum of the xj in absolute values, if I take it between m and n, it's still going to be smaller than epsilon. Right, now let's fix an epsilon and let us try to prove the same thing for the x pi j's. So what can I say? I can say that the inverse image by the bijection pi of the finite set 1 to n epsilon, well, it is a finite set itself with n epsilon elements, and I'm just going to call them a1, a2, until an epsilon. Now, this is a finite set. It has a maximum, which I will denote m epsilon. And what's interesting about it is that if I take a j which is above that m epsilon, that is to say that pi of j cannot be anywhere in that set 1 to n epsilon. So pi of j would have to be greater than n epsilon. Okay, let's give ourselves a j and a k both above m epsilon. We're going to need to consider the sum of the x pi l when L runs between k and j. And one thing I can say is that for all L running between k and j, pi L is certainly going to be greater than the minimum of the pi of n when n is between k and j, and it's going to be smaller than the maximum of the pi of n when k is between n and j. And this minimum, wherever it may be, because of the properties that we have here, is always going to be above n epsilon. Now, when I sum the x of pi L, and L runs from k to j, I have a certain number of terms in here, and all those terms have to be between the minimum of the pi n and the maximum of the pi n. So this sum is certainly smaller than the sum I would get if I did not forget any of the terms, and I summed the absolute values of xm for m running between the minimum of pi n, when n is between k and j, and the maximum of pi n, when n is between k and j. But now both this minimum and this maximum are all above n epsilon, so by the Cauchy property that I've had here at the beginning, I can guarantee that this is smaller than epsilon. And what does that tell us? It tells us that the sum of the x pi L converges. Okay, now we still need to show that this sum of the x pi j is equal to the sum of the xj. So how are we going to do this? We're going to give ourselves an epsilon, and we're going to pick an n which is very large, at least bigger than the maximum of n epsilon and m epsilon. Right, now we're going to compare the partial sum of the xj's up to that n and the partial sum of the x pi j up to that n. And the point here is, because my n is greater than m epsilon, this guarantees that somewhere between 0 and n, the pi j's are hitting every number 0, 1, 2, 3 up to n epsilon. So the first capital N epsilon plus 1 element in that sum are all cancelled with elements in that sum, which is to say that out of the first sum, we only have left, after cancellation, the elements above n epsilon. And in the second sum, well, we've removed a certain number of elements, but we don't quite know which ones. So we have a sum where j runs between 0 and n, but it's restricted to those elements where pi j is now above capital N epsilon. Okay, let's estimate this using triangle inequality. When I look at the first sum, it's smaller than the sum of the absolute values of xj, when j run from n epsilon plus 1 to little n. And when I look at the second sum, well, I have a whole lot of elements in there. Let's call them xm, but the m has to stay above n epsilon, and there's finitely many of them. They're going to go at most till the maximum of the pi j when j is between 0 and n. And now the point is, I'm looking at the sum of some xj's always for values of j's that are above n epsilon, and so by the Cauchy property, this has to be smaller than 2 epsilon. And now this concludes the proof. Okay, we now turn to the proof of the negative result, the second theorem in this video. We have a series that converges, but it does not converge absolutely. So the series of absolute value diverges. Right, and now we give ourselves an x real number, and we're going to have to find a bijection of the natural numbers such that the sum of the x pi j converges exactly to x. The first thing we're going to do is that we're going to decompose the natural numbers into two sets, s plus and s minus. S plus is going to be the set of all natural numbers such that xn is non-negative, and s minus is going to be the set of all natural numbers such that xn is negative. And so, of course, the union of these two sets is exactly the naturals. Now, I'm going to point out that both sets have to be infinite, because here is what would happen if one of the sets were to be finite. Right, if we assume that there exists a number n such that for all n in S plus, n is smaller than capital N, then what would happen is that after that number capital N, we would know that all the xn's are negative. But that would mean that the sum of the xj's, when j is greater than n, which we know exists because the sum of the xj converges, would be equal to minus the sum j equal capital N to infinity of the absolute values of xj, because all the xj's are negative. But then that would imply, because this sum on the left converges, so this tends to 0 as capital N tends to infinity, that this also tends to 0 as capital N tends to infinity. Therefore, the fact that the sum of the xj converges implies that the sum of the absolute values of xj also converges. But we know it doesn't by assumption, and so this is a contradiction. Okay, what have we contradicted? Well, we have contradicted the fact that the set S plus is bounded. So we have that the set S plus, the supremum of the set S plus, has to be plus infinity. In the same way, we could run the same reasoning for S minus, and so we also have that the supremum of S minus has to be plus infinity. That is to say, both the set S minus and the set S plus are infinite sets of natural numbers. Okay, let us give some names to the elements of S plus and S minus. I'm going to write the element of S plus as nj's, j in n, because that's an infinite set. And I'm going to write the element of S minus as mj, j in n. Again, that's an infinite set. And I'm going to order the nj and the mj such that nj plus 1 is greater than nj, strictly greater, and mj plus 1 is greater than mj, right? I've enumerated the infinitely many elements of S plus and the infinitely many elements of S minus. And what I want to show next is that the corresponding series, the sum of the nj and the sum of the mj, both have to diverge. That is to say, the sum of the nj is going to be plus infinity as a diverging sum of non-negative terms, and the sum of the mj is going to be minus infinity as a diverging sums of constantly non-positive, well, actually negative terms. Right, so let's do this by contradiction and assume that the sum of the x and j converges. Okay, let's look at a finite sum of xj's up to some number capital N. Now I can split it into two sums, two finite sums. The sum of the xj whenever xj is non-negative, that is to say when j is in S plus, I'm going to use this notation, the indicator function, to denote something that is equal to 1 when j is in S plus and equal to 0 if j is not in S plus. And then I have the finite sum with the indicator function of S minus to sum up all the xj's that have negative values. But this first sum is really a sum of x and j, j running from 0 to capital N, restricted to the set where nj is between 0 and n. So let's write it as the indicator function of 0n applied to nj. So once again, this is something which is 1 provided nj is between 0 and n, and is 0 if nj is not in that interval. So I'm only taking those x and j's that give me an xk where k runs between 0 and capital N. And then I can do the same thing for that other sum here. And that's the sum of xmj for mj in 0, n. Sure, but now remember that sum of xj converges. So this sequence, as capital N goes to infinity, goes to a finite number sum of xj's. And we have assumed, right here, that the sum of the xnj also converges. So if you send capital N to infinity, xnj, and you are now not restricting anything here, because you're summing up all of this non-negative xnj, then this also converges to a limit which is a non-negative real number. All right, but what is that telling me? It's telling me that the sum of the xmj also converges. Right, but what happened if I look at the sum of the absolute values of xj? I could do exactly the same thing as what I did with the sum of the xj's themselves, except the sum of the absolute values of xj from 0 to, let's say, capital N is the sum of j equals 0 to capital N of xj itself on the set where j is in S plus. And if I want the absolute value, I got to take minus the negative part, 0 to n, on the set where j is in S minus. But if these two things converge, both the sum of the xnj and the sum of the xmj, then this would have to converge as n goes to infinity to the sum j equals 0 to infinity of the xnj minus the sum j equals 0 to infinity of the xmj. But that is telling me that the series converge absolutely, which is a contradiction. Okay, so what have we shown? We've shown that the sum of the xnj cannot possibly converge. And of course, the exact same thing can be done for xmj. That is to say that the sum of the xnj, as capital N goes to infinity, has to go to plus infinity, and the sum of the xmj, as capital N goes to infinity, has to go to minus infinity. That's the only way you can diverge as a series of non-negative numbers here and just negative numbers there. Okay, now here is the key idea of the proof. When I'm going to construct my bijection, I'm first going to pick my pi1, pi2, pi3 to be n1, n2, n3. So I'm going to add positive terms until I get above the value x I'm trying to reach. And then what am I going to do? I'm going to switch to adding xmj's such that I start going back down until I go below the value x. And once I go below the value x, I'm going to keep moving back in the other direction, adding nj's. And I'm going to do that, and thanks to the convergence, I'm going to get closer and closer to x. And I'm going to proceed as follows. First, I'm going to pick an integer n0 to be the smallest integer such that the sum from j equals 0 to n naught of the x and j goes above x. Right? So I start adding the non-negative x and naught plus x and 1 plus x and 2, whatever many I need until I get above x. And I know I'm going to get above x because the total sum of the thing is plus infinity. So I can add whatever I need to get above x. But as soon as I get above x, I stop. Okay. And then I define the first elements of my bijection. I define pi naught to be n naught, pi 1 to be n1, until pi of n naught, which is defined as little n of n naught. So that defines capital N naught plus 1 elements. And now I'm going to pick some other elements of the natural numbers to keep defining pi of n naught plus 1, pi of n naught plus 2, and so on and so forth. And now that I'm above x, what I'm going to do is that I'm going to pick n1 in n to be the smallest integer, such that the sum of the xnj, j equals 0 up to n naught, plus the sum of the xmj, which is a negative term, j running between 0 and capital N1, goes below x. And I know I can do that, again, because the sum of the xmj goes to minus infinity, so I can subtract whatever is needed to get below x. As soon as I've gone below x, I stop. And now I'm going to iterate this procedure. Okay, now this defines the next elements of my bijection. I'm going to define pi of n naught plus 1 to be m naught, pi of n naught plus 2 to be m1, and I'm going to keep going until I reach pi of n naught plus n1 plus 1, which will be little m of n1. And now we can keep doing this by induction. So inductively, this defines what? This defines an increasing sequence of integers. Let's call it mk. And a map pi from the set 0 to mk until the integers for each k, let's call that map pi k, such that, well, either you've reached a point where you are just before x, and then when you hit a mk, you get above x, or a point when you were just above x, and then in the next step, you ended up below x. And the pi k is such that pi k of the set 0 to mk is made of a certain sequence of nj's up to a certain value, let's call it k of k, and a certain numbers of mj up to a certain value, let's call it lk, for some increasing functions capital K and capital L from n to n. Right? You keep on selecting either some nj's or some mj's to be the next elements of the form pi j, and you keep selecting nj's if you need to get above x because you're below it, or you keep selecting mj's if you need to get below x because you are above it. The question is then, as you do that, how close to x are you getting? Let's give a name to these two cases, case 1 and case 2. So in case 1, what can I say about the sum up to mk? Well, x is smaller than the sum from j equals 0 to mk of the x pi j, but that is equal to the sum of the x pi j up to mk minus 1 plus x of pi of mk. But then this is smaller than x plus x of pi of mk. Therefore, in absolute value, the difference between the sum of x pi j equals 0 to mk, and x cannot be larger than the absolute value of x pi of mk. That's triangle inequality. And that's in case 1, but the same holds in case 2 with the same reasoning, except, the inequalities are a little different. You get the x plus x of pi mk on the left-hand side. Right, but what can I say about x of pi mk? Now remember that by construction, pi of mk tends to plus infinity. We just kept it increasing and we have infinitely many choices. All right, so this has to increase to infinity. But because the sum of the xn converges, well, the limit of the xn has to be 0, and the limit of the xn is exactly the limit of the x of pi of mk as k goes to infinity, because pi of mk goes to infinity. Therefore, the error that we are doing here between the partial sum of x of pi j and the x goes to 0 as k goes to infinity. That is to say that this series converges, and it converges exactly to x, which was our conclusion.